Now let's look at impedance and admittance. The first thing, let's look at impedance here. We define the impedance Z is equal to V, the phasor V divided by phasor I. This is the definition, the ratio of voltage to current. Now for the phasor expression, if we put that in, we have Vm theta V divided by Im theta I. That gives us the impedance amplitude and the phase angle of the impedance, theta Z. Where you can see clearly that the amplitude of this impedance is the amplitude of the voltage divided by amplitude of the current, where the phase angle of the impedance is the theta V minus theta I. Now, why minus? If we remember that Vm, the phasor, can be also written as Vm e to the j theta V divided by Im e to the j theta I. So it's not hard to see the ratio of amplitude here. But when we're looking at the phase angle, we're looking at exponential divided by another exponential. That gives you e to the j theta V minus j theta I. So you can see that's where the theta V minus theta I coming from. For the unit, it carries ohms. And you can imagine that for Ohm's law, we have V divided by the volts divided by current, ampere, and that is ohms. So this is going to have to be exactly the same. So it's in ohms. Now, because the impedance has amplitude, has phase angle, so it must have the imaginary part. Because if I do express that in terms of the, we call rectangular expression, Z is equal to the Zm e to the j theta Z. We can definitely express that in terms of Zm cosine theta Z plus j Zm times sine theta Z. And so this is the real part here. And that is the resistance. And this, the imaginary part here, that's what we call, we use X, capital X to represent it. And this is called, this is called reactance. Where this is the resistance. So once we define the impedance, and we can look at in circuits. So now we're going to look at in circuits. The first thing we want to look at for a resistor, what is the impedance? Remember that V is equal to R times I. And so Z simply just equal to R. It's a real number. But for inductor, V is equal to J omega L I. So the Z, the impedance, is equal to the ratio of V divided by I, and that gave us J omega L. And of course, we can write this phasor form here is 90 degrees, and the amplitude is omega L. And you can see the impedance in here is frequency dependent. And this is what we call XL. Remember this is a reactance, and we call this inductive. Inductive reactance. For capacitor, and we have V is equal to 1 over J omega C times I. So the Z is equal to V divided by I, and is equal to 1 over J omega C. Now, if you write this to be the form of JXC as the reactance, which is in amplitude here, this is equal to negative 1 over omega C, 90 degrees. Now, where the negatives coming from? We notice that the J is in denominator. If we multiply by J here and J here, J times J is equal to negative 1. And therefore, we have a negative sign. And we can also write this as a 1 over omega C and negative 90 degrees. Where the XC is capacitive reactance. So once we know how to calculate the impedance for resistor, inductor, and capacitor, and the next thing would be very simple to look at the combination. What happens if we have the elements is connected in certain ways, and how do we combine them? So the next thing we're looking at here is the combination. And for series connection, when we have an element, this time we don't really need to identify what elements is in there, whether it's resistor, capacitor, or inductor. We all express them in terms of Z's. So we have Z1, Z2, and Z3. Notice that what we know is that the total voltage here, is equal to V1 plus V2 plus V3. So this is V1 across the element 1, V2 across element 2, and V3 across the element 3. And they all have the same, so the V total is equal to V1 plus V2 plus V3. Now they all have the same current, because in series connection they all have the same I. Therefore, if I want to express that V1 in terms of current and impedance, remember the definition, V1 is equal to I times Z1. And then the I times Z2 for V2. And I times Z3 for V3. They all carry the same current, so I can factor the I out. I have Z1 plus Z2 plus Z3, and if I divide the I on this side here, V total would be divided by I. That is equal to Z1 plus Z2 plus Z3. Notice this? That is the equivalent combined impedance. That's Z total. So therefore, for series connection, they're just simply adding like resistors. Now there's 3 of them. If you have more, you simply just adding them. That's in series connection. For parallel, where you have elements, again in this case, we don't need to identify what are they. What do we notice this time is that we have plus minus, we have voltage on everybody. This is exactly same voltage. But current might not be the same. So this total current comes in and going to split to I1 and to I2. And they're going to come out total I again. So in this case, we know the I is the one that get add up. That I1 plus I2, where we can express I1 in terms of voltage and impedance, and that is the voltage divided by impedance 1, that's I1, where the I2 is the same voltage divided by the impedance 2. Now, then you can see, if I write the entire thing, the I as the voltage, the same voltage here, divided by the total equivalent impedance, and you can see that in parallel, the reciprocal of the total impedance is the sum of the reciprocal of each individual elements that are in parallel. And I used the 2 as an example. If you have more of those in parallel, you simply just add 1 over Z3, 1 over Z4, and so on. So this is the combination, which precisely the same as resistors. So we can now look at the example. Here's the example that we have a couple of elements that combined in certain different ways. We have an inductor, and then we have 2 resistors, we have capacitors. What we need to notice is how they are combined, how they are connected before we can approach that problem. Now, first we probably wanted to find out what is the impedance of the capacitor. That is equal to 1 over J omega C, which is equal to a negative J 1 over omega C. Omega is 800 pi. And C is equal to 10 microfarad. Now 10 times micro is 10 to the negative 6. Impedance of the capacitor is equal to negative J 39.789 ohm. Now we do the same for the impedance L. That's equal to J omega L, which is J 800 pi times 10 times 10 to the negative third. The millihenry is milli is 10 to the negative third. Do that computation. We have J 25.133. We don't want to round it up too much now. Alright, now what we realize here is that 2 ohm resistor is in series with the capacitor, then in parallel with the 1 ohm resistor, finally is in series with the inductor. So the total, if we want to write down right away, that total Z is equal to the impedance of the inductor, which is ZL, plus that parallel connection here. The parallel connection here is, let's call this is R, this is R1. This is R1. Let's call this R2. So you can see the R1 times the combination of R2 and capacitor, that will be R2 plus impedance of this capacitor as one element now, and divided by R1 plus the combination, which is the R2 plus RZC. So now we can put the values in. We have J 25.133 ohms plus, here we have 1 times 2 minus J 39.8789 and divided by 1 plus 2 minus J 39.789. Alright, now there are 2 ways we can do it. If we find that ratio, let's look at this term first. Let's look at that term first. We have a real number here, and 1 times everything is just 1. So this just 1 just go away. And this is the we call rectangular expression. And the denominator is also a rectangular expression. It might be easier to convert the numerator to phasor and convert the denominator to phasor. And then phasor divided by phasor is a very easy computation. That's one way to do it. So let's do that. We have 2 minus J 39.789 divided by 3 minus J 39.789. That is equal to, converting to phasor, the amplitude is the real squared plus the imaginary squared. So that is R squared, that's a 2 squared, plus 39.789 squared, that's amplitude. And the phase angle is the tangent, inverse of tangent. That real part, negative 39.789 divided by 2, the real part. That's the phase angle. Now same thing for the denominator. We have the amplitude, that's the real part squared, plus imaginary part squared. The phase angle is inverse of tangent of the imaginary, which is negative 39.789 divided by the real part, which is divided by 3. So we convert them into phasor, and then we can find the ratio of the amplitude and the difference of the phase angle. So if we write this down, it turns out to be 39.839 divided by 39.912. You can see they're very close. And then the phase angle here in the numerator, the phase angle is negative 87.122. The phase angle is negative 85.688. And so we do that computation with, and we have 0.1. We have 0.9, 9, 8, 4, 2, 9. And the phase angle is negative 1.434 degrees. So that's one way to do it. And remember, when we do that here, we still actually have to convert this one into a rectangular coordinate, because we need to add that imaginary, we need to add this part. So we need to convert that into real and imaginary, so we can add an imaginary to this imaginary. So we do that, and certainly this is we know how to do it by now, is the amplitude times cosine of that phase angle is the real part. So that's the amplitude, and that gave us 0.998116 minus j, the amplitude times sine of the phase angle, and that gave us the 0.024991. So we need that. So finally, now we go put it back. We need to add that imaginary part. So the z is equal to j 25.133 and then plus 0.998116 minus j 0.024991. We need to combine this imaginary, and we're going to get 0.998. This time we don't need to carry that many. Then plus j 25.108. Certainly we're going to combine this into phasor, and so we have the real part squared plus imaginary part squared, take square root. We have 25.128, and then phase angle here is just the tangent of the imaginary part divided by the real part, and that gave us 87.72 degrees of ohm. The second part we do that here is that it's 89 is we can directly just convert that into rectangular coordinate by doing this, multiplying complex conjugate of the denominator. So we have 3 minus j 39.789 and multiply by complex conjugate is 3 plus j 39.789. And of course, we're going to actually do that on both the numerator and denominator. So simply we just multiply by a factor of 1. So this 3 plus j 39.789. And here we have 2 minus j 39.789. Now you can see the denominator this time is a real number. And numerator, we can work out to be a real part and imaginary part. By simplify it, it should give us exactly the same number as this one. So that's the second way that we can do that.